Okay, as you see, the topic is machine learning and Bayesian statistics. And basically, I will cover some basic idea and some background of today's machine learning problems, and I will put some focus on the Bayesian statistics. So first, let's look at what is machine learning. So basically, machine learning is data analytics technique that teaches computer to learn from experience. So basically, machine learning has four procedures. The first is pre-processing, and in this part is also called the feature extraction, which is the pre-process the input data. So, for example, if you want to do something like pattern recognition, maybe you want to resize the picture so that all the pictures have the same size. That is something like that is called the pre-processing. And the next is the most important part, which is the training. So in training part, we give it a training set X. Maybe there is also a target vector T. So which means if we give X, it should give us something like T. And after training, we will go to a testing part. And in a testing part, we are given the program a testing set, and the testing set is different from the training set. It must be different from the training set. And if the program gives us some correct answer, which is the same or similar to the target vector for the testing set, we will say our program has the generalization, which is the goal of the machine learning. So what can machine learning do? So basically, we can divide the problems into three kinds of problems. The first is supervised learning. The supervised learning, which means we give the program a training set and with its target vector. So we know the output for the training set. And for unsupervised learning, which means this problem we don't know what is the output, but we also give it a training set. But what's the result? We don't know. So that's the program to find the result by itself. And another one is reinforcement learning. This is very complicated. This is the problem which the program should learn to do some action according to the situation. So I will give some example for these three. The first is the regression. So regression is we give the program a set of data and it gives us a continuous output. So for here, this is a regression problem, which is, you can see this is a curve fitting problem. And another example for the supervised learning is classification. So for here, there are two kinds of data here. And one is 0 in red and the data in blue, that's 1. So there are two classes, and the program is doing something to classify the data into some categories. And there is a similar problem in the unsupervised learning, which is clustering. So the difference between classification and clustering is if we give the categories, for here that's 0 and 1, if we give the program, we know the output should be two categories. One is 0, one is 1. That is a supervised learning, which is classification. But if we don't give the classes to the program and let the program to find the groups by itself, that is a clustering, which is unsupervised learning. Another one is the density estimation, because we don't know what the density distribution looks like. So it's also unsupervised learning. So for here, this is the data from their experiment, and they use 6 Gaussian to get the distribution of the data. That is a unsupervised learning. And for the reinforcement learning, we know the machine should learn to take some action. So one most famous example this year is AlphaGo. So this, I think the name is Go. So this problem is a reinforced learning, and we also call this problem a credit assignment, because the core thing of this kind of machine learning problem is to give a credit to each step it takes. So let's look at the machine learning in our science area. So this paper is recent, it's a very new paper, and it is about machine learning for molecular and material science. And in this paper, they gave us some description of the application of machine learning and some errors may caused by the machine learning problem. And in this paper, there is this graph. So that is the evolution of the research workflow in computational chemistry. So this is our type 2. So first generation, we got the structure and we want to get the property. And in the second generation, they get the crystal structure and the prediction, the structure and the property. And with machine learning, if there is enough data and there is some formulas here and three kinds of type of learning, the techniques and model selection combined together is machine learning. With this, we can do something with the chemical and physical data and then predict the composition and structure and property. So we see the machine learning thing is much powerful than the old type of algorithm. And also in our biophysics, someone is doing the machine learning force field parameters, which is trained by the ab initio data. So that is automatically gets the parameter from the initial data. So you don't need to do anything but just let it work. Okay, and that's the overview for today's machine learning things. So then let's go to the Bayesian probability. So this is Bayesian. So today, basically there are two interpretation of probability. The first is the classical one. So the classical one we always use this. This is the frequencies of random and repeatable events. But for Bayesian interpretation of probability, that is different from this one. This is something like in-person things. It is reasonable expectation, representing a state of knowledge, or quantification of a personal belief. So basically, Bayesian interpretation is something like, if there is something, we want to get the probability of this thing happen in some condition based on our knowledge. But for this one is just from the things happened in our daily life and just do some statistics for the data. But this one is not. So one example, the key thing is the Bayes theorem. So if there are two events, x and y, and they are independent, so there is some sum rule here. So basically, the probability of x happen can be equivalent to the sum over the probability of x and y both happen. And here's the product rule, which means the probability of x and y both happen equals the probability of the probability of x happen times the probability y happen at the condition of x. And from the product rule, we can get the Bayes theorem. So if we just times the px to this side, this will be py in the condition of x times the probability of x. So this times this will become the probability of xy both happen. And for this side, it's the same. Just x happened in the condition of y times the probability of y happened. And this this times also this. So we can get the Bayesian theory from product rule. So why this is important for in our problem? I will show this later, but first look at this. So basically, if we have the D as the result we observe, which is the same as the target, I use the same symbol for the target vector, which is T. T1, Tn, these are the results we observe. And W is something like our assumption. So for here, this is still the Bayes theorem. So this is the probability of our assumption happen, or that's true, in the condition of we get this result, because the probability we get this result in the condition of our assumption is true, with the probability of our assumption divided by the probability of this result. So in Bayesian probability statistics theorem, we call this probability of our theorem as true called the parallel probability. And
so,
the thing is,
so the W's are the parameters of our model.
Yeah.
Okay.
Basically, it can represent the theorem of our assumption. And this is the probability available before we observe anything. And posterior probability P, which is this part, this is the probability obtained after we have observed something. So this is the, as I said, this is the probability of our assumption is true in the condition of we observe this result. And this term is the likelihood function. Basically, this is how probable the observed data set is for different settings of parameters vector W. So we can see the posterior is proportional to likelihood times the parallel distribution probability. So just stop here. So then we go to a simple example, which is a curve fitting example. So for a polynomial curve fitting problem, we have a training set, the x, which has x1 to xn, and together with its target value t. So we fit the data with the polynomial, which we call it y, x, w. W is our parameters. So basically there is n plus 1 w here, w0 to wn. And we all know the simplest way to get the polynomial coefficient is to minimizing the error function, which is this. So which is the difference between our model minus the vector, the target vector square. And by minimizing this function, we can get w. This is the most basic problem, and we can do some discussion about this. So this just only tells you how to get w, but the thing is, what is m? M is the order of the parameters. So what m is good? So from here we see this is some data point from a sine function with some arrows. And if we use 0, okay, it is very perfect. And equals 1, that's still very perfect. And if it's 3, okay, it seems better. But if m equals 9, so if it has a high order, we see this is not very good. So this problem is called overfitting problem. So to solve with the overfitting problem, there are two things we should look at. The first is the size of our data set. So still using the m equals 9. So there are 9 parameters here. So if we have 15 points, it looks not very good. But if we have 100 points here, it looks very good. So basically, the number of data points should be no less than some multiple of the number of the our parameters in the model. Sometimes they always say take 5 or 10 is a good choice. Another way to control the overfitting problem is if you have selected an M there, but you think maybe that is too, maybe that is not very necessary data here, enough data here, so you can do something like adding a penalty term to the error function, and that will look like this. So this technique is called regularization, and this is used in order to discourage the coefficient from reaching large values. If it has very large values and long lambda n equals minus infinite, which means the lambda equals 0. So this will give you some result like this. So why this happens? Because we see here the parameters are very big, especially for this term, for high terms. And with the penalty, we can see if this is minus 18, this will be much smaller, and actually the result is better. And if the lambda is infinite, so they are all close to 0. So this is a way to control the overfitting problem, but basically I don't know how to choose the lambda here. Okay, let's look at the curve fitting with Bayesian probability. The first thing is we use the Gaussian distribution in the following discussion. So first we assume the corresponding target value t has a Gaussian distribution with a mean equal to the value y. So y is still the polynomial model. So basically the probability of we get the target vector in the condition of we get the input x and the parameters, and this is which we call the precision parameter, which is the inverse variance of the distribution, is equal to a normal distribution with the mean at y and with variance with the beta, the inverse. Okay. So this is the starting point. Yeah. And if we think all the data are independent, so we can, so you see here, this t and x are not vector. So this is only for one set of data x and t. Oh. And for here, this is a vector and this is a vector. Because we think all data sets are independent, so this possibility can be times together of the normal distribution. And basically, we go back, I don't know if we don't go back. This term we can see it seems like, yes, this seems like the P, in the condition of W, which is likelihood. And take the line of the likelihood, and we can see here is a term which is similar to the error function. So basically, we can determine W by maximizing the log likelihood, which is this term. This term we call log likelihood, and we can see maximizing the log likelihood is equivalent to minimizing the sum of squares error functions, which is this one. Because in here the only terms depend on W is only these terms, and these terms is, we can say it is the same as the error function. And when we get W, we can easily get beta just to minimizing the log likelihood by take the derivative of beta, and we can get the beta, which we use NL to notation. This is from the maximum likelihood. So this is the persistent parameter, which is also our variance. So now we have our likelihood, and also we can see we can call this is the probability to get t when we have input x and with our maximum likelihood parameters and maximum likelihood variance. This is a normal distribution, and it can give you a distribution for the possibility to get t with our model. But this is not very enough for the Bayesian statistics. So for Bayesian statistics, our goal is to get the maximum posterior probability. So we see. So to get the maximum, to get the posterior probability, the first thing is if you remember, the posterior probability as proportion to the likelihood, which we get in the previous slide, just this. And there should be a parallel probability, which we make an assumption that it's like a normal distribution, which means it's at 0. Basically, you can change this number here, and it has its own precision parameter, which is variance of this distribution. So basically, the probability to get our result in the condition of given x and the parameters and the variance will be times over all these normal distribution points, which is our likelihood, and times the prior distribution, the probability is our posterior probability, and to maximum the posterior probability, we can give a function like this, and just to take the maximum of this function, we can get our parameters. But if you look at the form of this function, so if we go back to this, if we look at the regularization part, this term is lambda over 2 times the sum of the square of the parameters. This term is similar to the terms here. So only difference is the lambda here is just alpha divided by beta. So this is what we get from the maximum posterior. So, but for Bayesian, just to get a posterior is still not enough. So what we want is to get a distribution, the probability of get the test target vector t with the test training set, the test set x in the condition of we have the training set. So it's simple just to take the integral over the take the integral over the likelihood times the parallel probability over W. So finally, what we get is a picture like this, where the green line is the original data, where it comes from a sine function, and the blue points are the data points, which is the training data, and the right line is the mean value of that distribution. And the pink part is the area of the mean value plus minus the one standard deviation. So basically, from the Bayesian treatment, we can get a distribution at every point. So the classical way, so the maximum, the minimization of the error function will just give us a line. So basically, the Bayesian treatment can tell us the probability of the thing we want to get, and with a distribution, not like things like that. Okay, that's all. Any question?
Could you go back a couple slides? So basically, your last equation there, you were talking about minimizing what looks like the error function, right? So
no, not this one also. This one is focused on the error function with regularization.
Okay. So in order to basically all you're trying to do is set that W vector.
Yeah.
And then you're going to use those on, to define down something, power series or something. So when you talk about maximizing or minimizing it, you're talking about with respect to each of the elements of the W?
Yeah, basically the W.
Okay, so yeah, with each element.
For each W and maybe for alpha and beta.
Okay.
But this is only the terms in log this P, log this P, which contains W.
So does it matter how many elements W has? I mean, you mentioned before you don't know how many you are supposed to take.
Basically, if you want to get a proper number for the order of the parameters, one way is to just try different and to look at the behavior of the different m and choose the best one. So basically, in theoretical, first choose the m according to the size of data you get. This is starting point.
I mean, can't the method also tell you when you're overfitting? I mean, when you have too many parameters?
Yeah, if we have too many parameters, so basically if we have a number of 100 point the training set, basically we should choose less than 10 parameters if you want to get.
Yeah, but I mean that's a rule of thumb. But I thought that some of these methods also have a way to simply tell you that you have chosen too many parameters. So I don't know how, but
yeah, but actually in the pattern recognition book, as he said, a good way is just to compare the results from different. Yeah.
Okay.
That assumes you know something about the underlying data, right? I mean, because if I didn't have that sine function, let's say it's a lot more complicated, more than a sine function,
yeah,
there'd be a lot of noise in there to be relevant.
But the thing is, what you get, you don't know the green line. Yeah, that's the thing.
So you just kind of have to.
But if that is a very complicated original function, and if you only get 15 points, I don't think the data set is very enough.
Sure.
So basically, the more data you get, that's better. Actually, one of my friends is doing some project to predict the property of some condensed matter things, and he only gets 100 data set. And this is totally not enough.
So what you've been showing is that adding this ad hoc regularization term is equivalent to doing the Bayesian fitting with a Gaussian prior distribution.
So it's Bayesian fitting using the weight maximum posterior.
Okay, and the prior really says is that I don't really know anything about the parameters, but I'm pretty sure that they distributed around 0.
No, this is just a guess. This is just a guess.
Sure, but I mean, this is what you express.
Yeah, so that's why if we go back to the interpretation, it's representing a state of knowledge. So you should have some knowledge of the parallel distribution.
So
that's the starting point.
So the little that I know is that often you use just as a uniform prior. That's sort of a standard thing. You just say, all parameter values are equally probable. Here you're saying, well, you actually want large values to be much less probable.
Yeah. So actually, this method is based on many assumptions. But if you can do some training things, that will fix this.
So you showed one paper where they're using machine learning to do force field development.
Yeah.
So can you say a little bit more about this?
Basically, they should first have a large amount of data from the image.
Okay. Any more questions? Thank you. Okay, so that concludes